Okay, so this is a paper entitled A Structure in the Early Universe at Z of order 1.3 that exceeds the homogeneity scale of the RW concordance cosmology. I think that's quite a mouthful for a title.
That is not a catchy title.
It isn't really a catchy title, no, but the physics and the astronomy behind it is rather interesting.
Give me a better title.
The discovery of an implausibly large structure in the universe.
Nah, that's better. You should have written the title.
There's some big structure out there, a long way away from us, and they're saying it's the biggest structure that there is in the universe.
So this is basically a collaboration which are looking at quasars in the universe, so these very bright active nuclei in galaxies, not to study the quasars themselves, but because where there's a quasar, there's a galaxy, so they're a good way of figuring out where galaxies are in the universe, where the galaxies themselves are too faint to see. And they're mapping out these quasars in 3 dimensions to figure out whether they're randomly spread in space or whether they're clustered together, and if they are clustered together, how they're clustered together.
Such a large structure is incompatible with a universe which is homogeneous on very large scales. Homogeneous means you're in no special place, that what we see around us is representative of everywhere else in the universe. And so you don't expect, though that the argument goes, I'm not so sure I buy it yet, you don't expect to see such a big structure in a universe that is meant to be, on average, homogeneous.
So a quasar is a very, very bright nucleus of a galaxy. It's so bright it actually outshines the whole galaxy around it. The picture we have of these things is we believe that pretty much every galaxy has one of these massive black holes in the middle, and probably what's happening where you see a quasar is it just means that that black hole is particularly active, which means stuff is falling into it, which is making it light up. And so when these things were first discovered, they were called quasars because they were called quasi-stellar objects, which means they look basically like stars because all you see is this very bright nucleus of the galaxy. It's only when you look very carefully you see actually there's a whole galaxy around it. But they're very useful as sort of lighthouses because you can see a quasar at enormous distances all the way across the universe, even if you couldn't see a normal galaxy.
What is the scale above which you would say everything looks fairly uniform and below which you expect there to be structures? As you said, you know, you and I are quite different in many ways, and then you can just go up. You know, planets are different, stars, and then galaxies, they're different from one another. And you keep going to bigger and bigger scales, and you think, well, there's nothing homogeneous here. When I look around, things are looking quite different. But the idea is if you go onto large enough scales, and by large enough, we're really talking on scales of more than 100 megaparsec. A parsec is about 3 light years, so we're talking about 300 million light years. You have to go before you begin to sort of suggest that above that scale, things should start looking very similar.
So what these people have found is looking at the distribution of quasars in space. They're not randomly distributed. That's not news. But what they've actually found is that they form these incredibly large structures. When you start kind of mapping out the quasars, you find they form these enormous filaments. The latest thing that they found, which this paper is all about, is a structure where the longest dimension of it is fairly elongated, and the longest dimension of this collection of quasars is about 4 billion light years long. And bearing in mind that the entire universe is only about 13 billion light years across, so this is almost a third the size of the universe, this structure. So it's a huge collection of these things.
That sounds like the ultimate elephant in the room. That sounds like it sounds like it's the dominant beast of the universe.
And actually it causes a problem because the picture we have is that when you go to large scales, the universe is supposed to be homogeneous. There's this thing called the cosmological principle that says that one bit of the universe is really very much like another bit of the universe. And of course, if you've got a structure this big, it really means that one bit of the universe isn't very much like another bit of the universe because one bit's got this massive structure in it and another bit hasn't got this massive structure in it.
The big question is whether that is it real? Is it a real feature? I can't really comment on that. I mean, I just find it mind-blowing that the idea you can have 73 quasars linking across a distance of 4 billion light years. It just blows my mind. So how do they determine that they've got this structure? But let's assume it is. Let's assume it's a real structure. The next question is it compatible with an idea that the universe on large scales is homogeneous? It could be that we know there are fluctuations in a universe that's homogeneous. There has to be, because without those fluctuations we wouldn't form. you wouldn't form structures. So it could be that what we're seeing is just a rather extreme fluctuation, which is perfectly consistent. And in fact, there is a slightly smaller structure that was observed a couple of years ago, called the Sloan Great Wall. This was also seen in the Sloan survey. This is a structure of 200 to 300 megaparsecs, so it's not quite as big as this one. And even then, that was pushing the idea of homogeneity.
So here's this structure that they've identified, which, as I say, is about this sort of from end to end here is about 4 billion light years long. And so they've sort of played this game of join the dots. They've found where all the quasars are and found where all their nearest neighbours are, and used that to kind of span between them to say, look, it looks like there's a structure here. You have to be very careful when you're playing this game, because if you just threw down a bunch of quasars at random, once in a while they start forming things that look like structures. And so the exercise that you have to go through once you've found something that looks like a structure is say, is this consistent with just kind of a random collection of things and I just happen to have seen them arranged in this way? And the statistics they've done in this paper show that what they found is very unlikely to be just a random distribution of things. It really looks like they found a real structure in that sense. There's a collection of these quasars which are formed into this arrangement of quasars which is not consistent with them just being randomly splattered around the place.
The model that we're talking about, just to try and put some flesh to these bones, is the universe is very smooth on very large scales. So if I think of the matter distribution in the universe, I think of it as a mill pond. And that matter distribution is perfectly flat. The mill pond's perfectly flat. That's your homogeneous bit. But on top of it, there are these little ripples, right, coming from fish. And some of us are fish. And so these ripples are there. And those are the small fluctuations. So you've got the background homogeneous, everything's smooth, and then you've got the small fluctuations. And where you've got slight excess fluctuations, that means the gravitational pull. You've got slightly more matter. So from Newton's law, where the force of attraction is proportional to the mass, you've got slightly more here, that will cause things to attract to it. And then it will leave regions where it's attracting matter from. They'll be devoid of matter. They actually will create voids.
The force that we think shapes the large-scale structure of the universe is gravity. It forces things to collapse in certain dimensions, and so actually you end up forming these sort of sheets of things and filaments and those kinds of things, which we've seen all the time. When we look at galaxies in the nearby universe, we find they're not randomly spread. There are some places where there are clusters of galaxies, some places where there are none at all, some places where they form into these sort of sheet-like structures or filament-like structures. So presumably the physics is the same on these scales. What's forming these very large structures is gravity's forcing things to collapse in certain directions. The problem is that that's not what theory predicts, right? The picture we have of the universe says that gravity shouldn't have formed structures on these kinds of scales. So that's why it's starting to challenge our picture of cosmology, is that it seems to be there, but we're struggling a bit to come up with an explanation as to how it might have formed, which of course that's when science starts getting interesting, when you start finding things that you weren't expecting to find.
In that analogy you made with the fish or whatever it was making little ripples on our mill pond, what's the reality in the real universe? What's causing these fluctuations that allow large structures to form?
Okay, so this is where it gets really fun. All right, now we're moving back to the very early universe. How early? About 10 to the minus 35 seconds into the universe. That's really 0.0000034 zeros and a 1. Okay, seconds into the universe. And this is the period known as where the universe expanded exponentially quickly. And so the space expanded exponentially rapidly. And in that universe was a thing called a scalar field, a bit like the Higgs field, permeating the whole of the universe. And it fluctuated because of quantum mechanics, just like the Higgs field fluctuates. Randomly. And those fluctuations, the big difference that goes on here is that those fluctuations don't just remain small. Because the universe is expanding so rapidly, they quickly get they're grabbed hold of. I'm getting too excited. I'm speaking too quick. Slow down.
Ed, I will never accuse you of speaking too quickly.
These fluctuations get grabbed hold of by the expansion of the universe and stretched onto big scales, and those are the cosmological scales. And it's there that the initial seeds came from. So what we're seeing when we look at the large-scale structures in the universe, when we look at the microwave background fluctuations in the WMAP, and see these hot and cold spots, what you're actually seeing is an imprint of those very early moments, way before a microsecond, way before a nanosecond into the universe's history, when these fluctuations from the field emerged.
A big blown up projection of just a funny little wobble in a field.
Wow. And see the structures that we see. And what
there
they
probably
find
is
is
not
that they do
it's not a
something like 200
gravitationally bound
simulations,
structure in that sense.
and they
It's
find
just
in
that gravity has
155
started
of them or
rearranging
something
things. So even though
structures
they're all flying
of the
apart from each
size
other as the
that the
universe
Sloan Great
expands,
Wall had.